Alright, let's get started with the warm-up. Find a value of q that will make g of x continuous. So for x less than or equal to 1, we have a linear function. So maybe the graph is going something like this. It's a linear function for values that are less than or equal to 1. Then we have a quadratic, and hopefully if they do, we can make it where they connect. And then we have quadratic for values that are greater than 1, something like that. Okay, so what we're gonna do is it has to satisfy continuity, that the left-sided limit has to equal to the right-sided limit, and it has to be defined at 1. So if we actually just substitute x is equal to 1 for both pieces, and then set them equal to each other and assume that it is continuous, then let's do it like that. So it'll be q times x is 1 plus 3 has to equal to 1 plus q squared minus 10. Q times 1 is q, so we have q plus 3. And then we can FOIL this out. So this is going to be 1 plus q times 1 plus q minus 10. So continue on, q plus 3 is equal to 1 plus q plus q plus q squared minus 10. Bring it down. So it looks to be that, let's show you how, it's a quadratic. So maybe we can move everything to one side and factor if it's factorable. So let's move it here, and then minus 3. So cancel, 0 is going to equal 2. 1 take away 3 is negative 2. And then let me erase this. Let's continue on. I should have already. So this is going to be q plus q squared minus 10. These ones are also like terms. Now I can put it in from biggest power to lowest. So the q squared plus q, that's minus 12. And now we can factor, and hopefully we can find a q value here. Let's see, factor, that would be what? Plus 4 minus 3. So the possible values of q could be q equal negative 4 or q equal 3. So which one is it? Is it q equal negative 4 or q equal to 3? Is it both, or is it just one of them? Why don't we just plug it in? If we plug in, let's plug in negative 4 and see what we get here. If we plug in q is negative 4 here, then we get negative 4, and then x is 1, so it's just negative 4 times y is negative 4 plus 3 has to equal 2. X is 1 plus q is negative 4 squared minus 10. So we got this equal negative 1 has to equal 2. 1 plus negative 4 is negative 3. That would be 9 minus 10. And then negative 1 is equal to negative 1. That is okay. If we do q equal to 3, so then we got 3 times 1 is 3. 3 plus 3 is 6. So we're going to get 6 is equal to, x is 1, and I'm saying q is 3 squared minus 10. So x is 1, q is 3. So then we're going to get 6 is equal to 16 minus 10. So 6 is equal to 6. So it says that both of these Q values work. So it has two Q values that would work. So this is lesson 112, confirming continuity over an interval. The following types of functions are continuous at every point on their domain. Polynomial functions, example, a linear function is continuous everywhere. A quadratic function is continuous everywhere. A cubic function is continuous everywhere, on and on and on. It's actually on the reals as well. It's on its domain and on the reals. Exponential functions, also this one is continuous everywhere and on the reals, on its domain and on the reals. Trig functions, the sine function, it goes up and down forever, and it goes forever, forever, forever. That's on its domain and on the reals. It's continuous. Tangent function. Now we're getting where this one is on its domain only. So because the tangent function does have some vertical asymptotes. So this one, let's see, where does it go? How can we figure out where it goes? Tangent of x. So what's tangent of, let's say tangent of 0. So tangent of 0 will equal to unit circle. This would be x and y. X is 1. So this is 1 and this is 0. So tangent is y over x. So this one would be 0 over 1. So this is okay at 0. So then the graph does something like this, but then it has asymptotes here, and then it just continues going like this, and it has asymptotes. So it is not continuous on the real, but it's continuous on its domain. So this is one that is continuous on its domain. On these other ones on the reals, on the real number line. Rational functions. This one as well. Function goes something like this. It has a horizontal asymptote, and then also has a vertical asymptote. So it is continuous on its domain, but it's not continuous on the reals. Natural log function, any kind of log function, goes something like this. Then it has a vertical asymptote here at x equal to 0. So it will never cross here. So it's continuous on its domain, but not on the reals, because it doesn't exist here. Radical function. What's a radical? A radical function goes like this. Starts here, and then it just shoots out this way. So this is continuous on its domain, but not on the reals. So what are the three scenarios to watch out for when looking for a restriction on the domain? You got to watch out for the denominators. The bottom of a fraction has been a common theme for the first 3 weeks. You got this rational function. So for this rational function, the bottom of a fraction cannot equal to 0. The bottom of a fraction cannot equal to 0. So that's what you're looking at. The bottom of a fraction cannot equal to 0. So x cannot equal to 1. So even root radicals, the inside of a radical has to be greater than or equal to 0. So this is how we attack it. See, a rational, the bottom can't equal to 0. For a radical, the inside of a radical has to be greater than or equal to 0. So if you solve this, you add this, so it'll be 2x has to be greater than or equal to 3, divided by 2, x has to be greater than or equal to 3. So that is the restriction on the domain, 3/2. And for logs, the inside here has to also be greater than or equal to 0. So we're going to say that x minus 3 has to be greater than or equal to 0. Because of the function, natural log goes like this. And then, so this is a very classic total. And it's not equal to 0 then, because it will never cross this. So it will not be equal to, so it has to just be greater than 0. So it has to be x minus 3 has to be greater than 0. So you add 3, so the x equal to greater is the restriction on the domain. So let's find the domain of each function. In reality, this is just pre-calculus. So we attack this problem saying if we just want to find the domain of the function, we attack it by just saying that the bottom cannot equal to 0. So x cannot equal to 0 and we're done, basically. So it's all reals. X cannot equal to 0. If we're talking about what the domain is. Domain. This is set notation here. Sure you're familiar with set notation from pre-calc. Let's move on to the next one. In number 2, we got 2 problems. The bottom, x cannot equal to 0. That's a problem. And on top, x plus 5 has to be greater than or equal to 0. So we got x plus 5 has to be greater than or equal to 0. So minus 5, we got x has to be greater than or equal to negative 5. So if you put this on the number line, and you look all the values that are greater or equal to negative 5, here's negative 5, this is 0, this is 5. Greater than or equal to negative 5 goes this way. Well, it cannot be this anyway, so already x cannot equal to 0, so we don't care about this. This takes care of even that problem over here. So x is greater than or equal to, let's see. No, actually, we have to jump it because it cannot equal to 0. Yeah, that's a problem. So it is okay, this is the domain, but then we have to jump it because it cannot equal to 0. Yeah, that's the problem, it cannot equal to 0. So add 0, it cannot equal to 0. So this one has to be a hole there. Let's clean this up. So it has to jump. So it has to go here, open, and jump, and then it's forever that way. So this is the domain here. So the domain will be, if you want to put it in interval form, you're going to say that including negative 5, all the way to 0, not including 0. Then you say union, or better yet, well, they prefer comma in the AP. So let's, instead of union, let's do comma. Comma, not including 0, to infinity. It's going to go to positive infinity. This is the domain. This one we said that x minus 4 has to be greater than 0. So we add 4, and x has to be greater than 4. So this is the domain, all values that are greater than 4. Or you want to do interval notation, you're going to say 4 to infinity. And they're both valid. Let's finish problem number 4. Where's